Hey guys, welcome to a new video. In this video here, we're going to talk about vector databases. So we're going to cover the theory and how vector databases work under the hood. Then we're going to see some practical examples, how we can use them for similarity search, how we can create embeddings of different types of text. And we're also going to see how we can use them for building RAG-based systems. So when we're talking about like real world LLM systems, it is often RAG-based systems. Just out of the box, LLMs are generating a lot of random stuff and also hallucinating. But if we're using RAG-based systems, we can use documents. So let's say that we have a ton of different documents, could be PDF files, text files, whatever text files that we want to embed. Then we can use that information, feed that information into our LLM together with our prompt. So we're going to have our query, we're going to query from our vector database, we're going to have our prompt, we combine that, and then we can have our large language model generate output based on factual information. So we're going to cover the whole pipeline. So let's now just talk about vector databases in general, how they work, what type of information can we actually store them, what are the advantages when we're using vector databases, especially when we're talking about AI applications. So you guys are probably familiar with all the different database types out there. So we have like SQLs, which is for structured data. So again, that is useful for a lot of different use cases. But when we're talking about AI, we're talking about scalability and also query speed. And we get a really good performance trade-off with speed and performance when we're using vector databases. So that is the ideal database for AI applications and especially RAG-based systems. We also have NoSQL, which is basically just like for documents and unstructured data. So often in real-time applications and so on, we will be using NoSQL. So another database which is normally used is a graph-based database. So normally you just store the information in different nodes and then we have edges connecting that. So we can have like different documents, we can have different structured data in each node, and then we can connect those between connections with the edges. Then we can create a whole graph-based database which has connections in between. So we have these three different databases, and now we also have vector databases, which we're going to cover in way more details and how we can use them in a practical use case. Basically just to take documents, it could be text file, PDF documents and so on, how we can divide them into chunks, take all the text, do embedding. So we actually need to have them in numerical values, which is what an embedding is. So we have different embedding models for that. In this video, we're going to use OpenAI's embedding model. I'm going to show you how we can use the API, do it directly in code. So we basically just need to take some text, throw it into the OpenAI embedding model, and then we get an n-dimensional vector out. So vector databases is really good for AI applications, and we're working with embeddings, which is basically just an n-dimensional vector. So if you want to visualize an embedding, we can either do it in 2D and 3D. And if we just do it on a very simple level and do it in 2D, then we just have a single point. So every single embedding we have will just be a single point, and then you can imagine having like an n-dimensional space, and then we just have a single point representing that embedding. So that could be like a whole string, could also just be individual characters or words. And when we're talking about vectors, it is basically just a vector pointing to that point. So if you have like the center of our coordinate system in an n-dimensional space, then we have a single point, and then we have a vector pointing to that point in our embedding space. So when we have the n-dimensional space, we're talking about an embedding space, and then we have each individual embedding. So when we have a whole document, could be a text file, PDF file, then we actually need to do the embedding. We need to convert it into an embedding space where we have numerical values, because then inside of that embedding space, we can both do similarity searches. We're going to go over that. I'm going to show you examples in the code directly, how we can do the embedding, how we can do similarity search between different embeddings, and how we can use that in a real world AI application for RAG-based system. So already have a video where we cover like the RAG-based system in more details. We have a Google Colab notebook where we write the code out each individual step. In this video here, we go way more into the details of how databases work and how we can do the embeddings on our own end, similarity searches, and then we're going to test out the RAG-based system at the end as well on new documents. So definitely check that video out as well. But this video here is really good for understanding how AI systems work under the hood. So once we have all our embeddings inside a common embedding space, then we can actually just do distance calculations. So we have different distance metrics, similarity metrics, and so on, where we can calculate the distance between 2 points or 2 embeddings in that space. And by using that, we can also do grouping, we can do clustering and so on. So let's say that we have some text and we have a query and we want to match our query to specific words or documents that we have embedded, because that is actually like the fundamental thing about RAG-based systems. So we have our large language models, they can generate text, but it doesn't have any information at all. It has just been trained on a large scale data set or fine-tuned on a base model. If you want to incorporate factual information, act like documents and so on. So if you have seen chatbots, different companies having chatbots, they have a bunch of different documents, they embed it, then they act like integrate that together with the large language models, and that is a RAG-based system. So once we have our embeddings inside the space, we can do searches and so on, we can do queries. So let's say we have a query, what is a neural network? Then from the query, we create an embedding based on the prompt that we have thrown into our chatbot. So it's going to take the query, then it's going to do similarity searches with the retrieval-based system in that embedding space, and then it's going to see what are similar to the prompt that we have given. So if we want to go over an example, let's say that we have a prompt, we throw into the system that we want to retrieve the information from the last 4 presidents in the United States. Then we have a bunch of documents inside of our embedding space. We're going to take the embedding, and then that embedding would actually be similar or like very close to other embeddings in that space. And then we're going to pull those embeddings which are close and similar to the prompt that we have given. We're going to take them, combine them, and throw both of those queries into our large language model. And then based on both the prompt, but also the information from our documents, the large language model is going to use that information to give us an output. So now we're actually like able to get factual correct outputs from our large language models. And that's how we can get all the powerful stuff out of the large language models and the chatbots. So it's way more scalable, way faster to retrieve information. And that is essential when we're talking about like real world AI applications. So now we've covered the technical details about vector databases, why they're good, why we should use them for AI applications. So right now let's go in and see how we can actually create a database, a vector database. Then we're going to go over the different kind of tools and frameworks that we're going to use. And we're mainly going to use LangChain and also OpenAI for generating their embeddings and the large language model, and then LangChain for basically just chaining together all the different components. So we can both use LangChain to chain together like multiple different outputs from large language models, but we can also use it now for handling our data and basically just chaining together data and large language models, and then we can generate a response with a RAG-based system. So right now I'm just inside Google. Let's just search for data stacks and let's take a look at their vector database. So right now I'm just going to open up the front page. You can go in, sign up and try for free. So right now I'm just going to sign in. You can also go through their documentation, but I'm going to show you each individual step of how to create a database and also how to connect to it inside code. So right now, the only thing that we have to do is create a database. So right now, we're just going to have YouTube test, and this is the database that we're going to set up. So UYT_test. We can specify the provider here. Let's just go for AVS. The region here, we can just choose whatever is available. We just need to hit create database, and it's going to take care of all of it. In just a second, we're going to set up our database. Right now, it's just initializing and might take a few minutes. After that, we get all information about like how we can set it up, the tokens, all the security checks and so on that we need to take care of, and then we can connect to it directly inside code. So right now, while our vector database is initializing, let's go in and take a look at the OpenAI and LangChain documentation, because then we have everything. We can take the code snippet, throw it into our own custom Python script from scratch. I'm going to show you how we can set up this whole system, both how we can create embeddings, do similarity search, and then at the end, we're going to create this RAG-based system, but we already have a video covering like the whole pipeline with that. So right now, I'm just going to dive into it. Right now, we can go over to the embeddings. We both have text generation, function calling. This is just the OpenAI API for the different GPT models and also the embedding models. So let's now go down and take a look at the embeddings. You can read about like what are embeddings, but I already went over all of that. So we can use it for search, clustering, recommendation, anomaly detection, diversity measurement, and also classification. So you can also see how to get the embeddings. We can see the different types of embedding models. So you can also just make a curl request to the OpenAI's endpoint, and then you can throw in the document, you can throw in the text that you want to embed, and you'll get the embeddings out directly. And you just get a response where you can extract all the information inside the JSON file. But again, then you will have to do this individually inside the terminal. I'm going to show you how you can do it in code. So we can store the whole document, take a whole document and take all the text within each document and do the embeddings in there. But the whole point here with doing the embeddings is that we have some text, and then we're going to have an n-dimensional vector, and that could be like hundreds, if not thousands of values or dimensions inside of that vector. So down here at the bottom, we can actually see the dimensions for the embedding vectors that OpenAI is going to return for the different embedding models they have. They both have a small and also a large model. You can also reduce the dimensions of the vector by just setting a parameter. Could also be that you don't have too many documents, or the task that you're trying to solve is not too complex, so you don't need like that large embedding space. You can have like a more dense one, still be able to do your similarity searches in there. If we scroll a bit further down, we can then see the embedding models. We have the pages per dollar. So this is how many pages we can extract per dollar. And we have the performance and the maximum input. We have the small, large, and ADA model, and we're just going to use one of them for our specific example. If we scroll a bit further down, we can then see the examples that they're giving for the use cases. And right now, you just make an API call, you take your request with the text that you want to create an embedding of, and then you get the response back. Here you can read about like how you can reduce the embeddings, question answering using embedding-based search and so on, but we're going to cover that in code and also with LangChain instead. So you can do all of this with OpenAI, but again, LangChain just makes this significantly easier to play around with. We're just going to use the OpenAI's model. Let's now dive into LangChain and see how we can use that. So if we just go inside the LangChain documentation, because that is what we're going to use to combine all of it together. Over to the left here, let's just go inside the components. They also have a bunch of different use cases, but let's go inside the components. So if we just take a look at it, we both have our document loaders, so CSV, HTML, JSON, PDF, text file, and so on. We have the splitters, so how we can split the files into different chunks. We have our embedding models, and we also have our vector stores. So this is pretty much what we've been using and going over throughout the whole video. So we load our source data, then we load, transform, and embedding. We have our vector store with data stacks with the Cassandra vector database. We have our embeddings, query vector store, where we actually just have our query from our prompt. So we take our prompt, we take our data, then we combine that. Also inside our vector store, we retrieve all the information with similarity scores, and then we can use that to feed it into our large language model that will then generate the response based on our source data and also our query. So right now, let's just go down and see how we can get started. We need our OpenAI API key. If we go inside OpenAI's documentation again, go over to the left, we can go in and take an API key and generate a new one. So the only thing that you have to do here is go inside the API key, generate a new secret API, generate the API key, copy paste it directly into the code that we're going to use in just a second. So while we've been going through the documentation for OpenAI and LangChain, let's now go in and see that our database has been initialized. We're ready to go and it's up and running. We can see it's active up here at the top. So let's go up and take a look at the connection details in the top right corner. We get the Python client, TypeScript client, and also Java client. The only thing that we need to do is pip install AstroPy. So again, this is an AstroDB. So this is how you can actually go in and connect to it. You can generate a token. You just need to pass in your token to the data API client. It's going to set up the connection automatically, and then you can start using it in the code. So I've just opened up my code editor. I have a Python script here so we can generate embeddings, and we also have a couple of text files. So right now I just have a generate embeddings, and then we're going to have a rec system Python file, and that is empty for now, and we're going to set that up in just a second. So we have a GPT PDF file here. I'm just going to open it up, and I've also converted it into a text file. So this is just a paper for the GPT-4 model. I'm going to pull it up here. So this is just a technical report for GPT-4, and it is 100 pages with a bunch of text, references, resources, and also appendix. So right now I've just converted it to a text file as well. So we have gpt.text, and we have everything in here. So every single line of text, we have it inside of our text file. So that is around 6,000 lines of text. Divide that into chunks, create embeddings based on that. So right now we just set up our environment key here. So our OpenAI API key. Then from LangChain, we're going to import the different document loaders. So those are the document loaders that I showed you inside the documentation. We both have a text loader, PyPDF loader, or whatever document format that you want to load in. Then from LangChain OpenAI, we're going to import OpenAI embeddings. You just need to pip install all of these ones here. So both LangChain underscore OpenAI, LangChain underscore Chroma, LangChain, and OpenAI, and you're good to go. Also the pip package from the AstroDB, and then we're pretty much good to go. We have everything installed with just a few pip installs. So right now we also have our character text splitter. So inside we have our text splitters from LangChain. We saw that in the documentation as well. We have our character text splitter. So just going to take each individual document, take the text, split it into different chunks, then we can throw that into our embedding model. And we also have Chroma here from LangChain. So right now we're just going to set up and initialize our text loader. We throw in our gpt.text. We need to specify the encoding here, or else it's basically just going to throw an error. So we need to make sure that we're using the correct encoding based on our system and the text file that we have as well. Then we can call this load method on top of our text loader, and we have our raw document stored in this variable. Then the next thing that we have to do is set up our text splitter. So we have our character text splitter. We need to specify the chunk size. So this really depends on like how large chunks do you actually want to divide your document into, and also our chunk overlap. So instead of just having like very rough chunks that we just split into it, then we might actually like end up splitting in the middle of a sentence, very important sentence, and that could actually cause some problems when we want to generate responses later on from our large language model based on factual information. Let's say that we just have like a sentence describing something and we just cut it in two, and we're not really retrieving that information once we're pulling that from our large language model in our RAG-based system. So we can specify a chunk overlap as well. So basically just we divide our whole sequence into a number of chunks, and then we just specify how much overlap we want to have inside of those chunks. So we have our text splitter, we have our raw documents, and now we can create our act like documents, split our documents, throw our raw documents into it. We have our text splitter, and now we have our chunked up documents. Now we can take that from Chroma here, from documents. So this is just another DB, but we can also do it with Azure DB, which I'm going to show in a second. This is just the example from LangChain. So right now we have our OpenAI embeddings. We disallow special characters. We have our documents. It's going to generate the embeddings. And then we have our database that we can then use to do similarity search, connect to our RAG-based system, and so on. So just open up a terminal as well. We can just go down and run the Python script directly. First of all, we just need to specify our OpenAPI key. I have it over here to the right. So I've just copied it now. I'm going to paste it, hit enter, and then it's going to set up the whole system. So right now it's just dividing it into a number of chunks. So we can actually see that it divides it into chunks larger than I have specified. And we will probably also have our chunk overlap. So this just took a couple of seconds to run. Now we have taken the whole document with 100 pages, divided into chunks, made embeddings with OpenAI, and then we're good to go. Now we have our database that we can use for our similarity search or our RAG-based system. So right now we can just try to do similarity search inside of our database. So we just specify a query that we want to set up. So we can just say, what is GPT-4? And have a question mark. So this will be our query. Now we can go in and do similarity search based on this query in our database. And again, we can also use the Azure DB. I'm going to show you that in just a second. These are just examples from the OpenAI and LangChain documentation. So then we'll have our documents here. We have our DB. We can connect to that and do similarity search. There we go. We can even go in and do it by vector. So if we have our query, we embed that into an embedding vector. Then we can also specify that and just have two embedding vectors and do similarity search based on those two. So here we just need to throw in our query. There we go. And that's pretty much it. Now we can just print our docs. Need to take the zeroth element of that and have our page content. Again, you can just have like a dot here. You can see all the different attributes that you can access directly in here. So this is the page content, and we can now just print it, and we should be able to extract the similar documents inside of our database based on this query. So what is GPT-4? Let's now just run it again. Throw in the OpenAI API key. Just dividing into chunks. Doing the embeddings. Of course, you will just need to do the embeddings once, then you have the database. But right now I'm just running it. It only takes a few seconds. Also just to show like how fast this is. So right now we have our query, we have our database, we do similarity search. So right now it's basically just pulling all the docs, all the text, which is actually like similar to the GPT-4 model. So what is GPT? So this technical report presents GPT-4, a large multimodal model capable of processing image and text inputs and producing text outputs. So here we basically just get the response, what is a GPT model? So this is just pulling the information from the database based on a query. So we can actually say that this is useful just out of the box for doing similarity search and having like a search engine. Then we can take these documents and then throw it into our large language model so we can generate better outputs and format it in different ways, whatever we like, and delete some of the parts here which is not necessary with references and so on. This is just a raw text that is extracting from the database. So this is how we can do similarity search. We can also go in and do embeddings. So right now let's go in and take a look at how we can create an embedding vector. We have our OpenAI embeddings, and then we can call embed query. We can both do embed documents for whole documents, and we can also just have a query. And this is how we can just generate embeddings based on a single string. There we go. We just need to pass that in, or the variable that we have, and then we should be good to go. We can even go in and print the embedding vector, and we'll be able to see all the values inside of that. So that will be a large n-dimensional array. print embedding vector. There we go. And now we can go down and do the exact same thing as we did up here. We just need to call another function. So we have our docs equal to db.similaritySearch, but now we're going to do it by vector. So we can also use similarity search by a vector with relevant score, with a score and so on. That is also very helpful because again, if we want to get factual correct information, we want to make sure that what we're querying from our database based on our query, we want that to be as similar as possible to the query, so we have the correct information all the time. So we can both get the similarity text, but also the similarity score, which is very useful. But right now, let's just skip the score for now. And now we just need to pass in our embedding vector. There we go. And we can, again, just print the docs. So I'm just going to paste that. There we go. Now we can rerun the program and it should be able to go in and do all of it for us, copying the OpenAI API key. There we go. It's going to load in all the stuff, chunk it, and create our embeddings. It extracts all the information. And now here at the end, it's going to print out the whole embedding vector. So all these values are the n-dimensional embedding vectors. So these are just numerical values. All of these values here are just representing this query. So this short string is embedded into this n-dimensional vector inside of our embedding space, as we explained earlier on. And then it's just going to pull all the information. It's going to extract the exact same information because it doesn't matter if we throw in the query, it extracts the information, does similarity search based on the query or the embedding vector, because that is basically just one-to-one based on the embedding model that we are using. Okay, so now we know how we can take our document, divide it into chunks and so on, do embeddings. Now we need to connect to the Azure DB vector store. So we also need from LangChain underscore Azure DB, so they have integrations directly with LangChain as well. So again, you just need to pip install this and you're good to go. Then we can import Azure DB vector store, just as we were using the vector store before. All the exact same methods and so on can be used, like how you can add text, add documents to the vector stores directly, so the vector database, but we can also call the similarity search based on the embedding vector and so on. So all of the functionality is the exact same thing. It doesn't really matter what database that you're connecting to, but this Azure DB is really easy to set up. We just need to have our token, endpoint, key space, and then we're pretty much good to go. So I specified the token here. I've also specified the endpoint. So you can find all that information inside the website. So the endpoint is basically just the server that we're connected to, or like the endpoint, and then the token, you can generate that inside the connection settings. So here we're pretty much good to go. We're just going to go with the default key space and store that in there, but you can also create other namespaces or key spaces as well. Now we're going to create an instance and actually connect to our Azure DB vector store. So we can do our embeddings directly inside of that as well. So we just need to throw in the text, documents, and so on. It's going to take care of all the embeddings for us. So we don't even need to set up all the other code up here just to show the intermediate steps. So this is actually what it's doing under the hood, but Azure DB and DataStax takes care of all of that. So we have our vector store, we have our database, we are now connected to it. We throw in the OpenAI embedding model that we want to use. You can specify the different arguments and so on directly in here. Or if you have other embedding models that you want to use, we specify the namespace, the collection name, the token, and also the API endpoint. Now we have a connection to our Azure DB vector store. Now we can go down and add text, documents, and so on directly into it. Right now, we're just going to take the output from our similarity search based on what is GPT, and then we're going to get the inserted IDs. We print the length of it just to see like how many documents have we inserted into our vector database. Then we go inside the DataStax website and actually see the live information being stored in our vector database. Then we can go ahead and create a rack-based system based on that. It is the exact same thing that we have done right here. The only difference is that we now store information in the vector database. So once we shut down a computer, once our program is not running, we will still store all the information, so we don't have to do the embeddings every single time we run the program. So we can take a bunch of different documents, hundreds, thousands of documents, throw it into the vector database with the embeddings. We can do similarity searches if you want to use that for specific use cases, or we can use LLMs, take the query, take the queries from a vector database, combine them and have our large language model create and generate reliable outputs that can be used in real world LLM projects. So right now, after we've done that, we're just going to do similarity search here just to show you guys that we can call this functionality. The query will be the exact same thing. So what we'll have in our database is just going to be the text that we already had. And then we're just going to do our similarity search based on what is GPT-4. So right now we have everything. We just have the connection to it. I can then just go down and run the program again. It's going to run everything up at the top. I'll just have to take the OpenAI key again. You can also just set this an environment variable, so you don't have to do it every single time, or specify it up here at the top. So right now it's just dividing into chunks, doing the embeddings, but now we're actually connecting to the AstraDB vector database. So it might just take a few seconds, probably just 10 seconds for being able to connect to it. You can also have this in Jupyter Notebook, just connect to it in the start, and then you can always just add new text and also documents directly if you have different folders. Also, if you have different types of documents. The good thing about embedding spaces is that we can embed different types of data. So we can both have video embeddings, where we basically just extract individual images from videos. We can take image embeddings. That will also just be like a vector with numerical value, n-dimensional array. We can take text, audio. Every single data format inside your computer can be embedded into a vector, and then we can throw that into the same space. So we can both have video, we can have images, audio, even like 3D point clouds. And this is how we create these multi-model models. Basically just take different domains of data, create embeddings into it, have it inside a common and unified embedding space. Then we can do similarity searches. So this is how language and vision models work together as well. We just need to get our information, all our data into the same space, and we can apply all of these techniques. We can have our vision models, we can have our large language models, natural language processing, and we can prompt all of it, and we can store huge amount of data, retrieve it fast, make it scalable by using vector databases. So yeah, here we go. We're pretty much good to go. We've inserted 2,500 documents. We have also done the similarity search, so we will be able to get our results, and will be the exact same output as the previous ones here, because we retrieve and extract the same information. Doesn't really matter what database we're using. Right now, let's now go inside our DataStax dashboard again. We can see some key metrics of the different requests that we're sending to our database. We can see the number of total throughput, collections, the total records, and so on. But if we go inside the Data Explorer, we have our namespace that we connected to before. So we have our default underscore key space, the number of dimensions. So this is the dimensions of our embedding vector from OpenAI. So it's using the small model cosine for similarity search. So that's the most common similarity distance function that is used. A lot of research is going into like how can we do optimal different types of similarity searches and so on. So that is a whole field in itself. If we go down and take a look at it, we then have our test collection. You can create multiple collections and also different key spaces. So you can always just create a new key space or like a new namespace. Here we can see our collection of data, our table, and also JSON files directly. Now we can see that we have our search, vector search. We have our vector with all the numerical values, which we had inside of our program as well. It also assigns a unique ID, so we can retrieve the information and do indexing into our database. Here we can see the content that it's storing. So this is the embedding, this is the content, and this is the corresponding embedding in numerical values, so we can use it inside of our computers. So I hope you guys have learned a ton in this video here. It is a lot to digest. It is also pretty long, but it is really important to understand how vector databases work and also how they're used in generative AI applications and projects with RAG-based systems, because pretty much every chatbot that we've seen out there is based on this RAG, so retrieval augmented generation. Definitely try to understand like how this work under the hood, and then come up with some cool simple applications and projects, because that is where you will learn the most from. I hope to see you guys in one of our upcoming videos. Until then, happy learning. So we also have an AI career program if you want to learn how to land AI jobs and get AI freelance work. I teach you everything in there. We have programs, all my technical courses, weekly live calls, personal help, and I'd love to have you guys in there, help you out in any possible way. You can check out the program down in the description and the community, and then I'll just see you guys in there.